What I want to look here is what I want to look at here is nuclear equations. Now, you hopefully all in your earlier days saw things like this, which was a carbon, and the number here was the atomic number, and the number above was the mass number, which is protons and neutrons. So if you want to know the neutrons, you just subtract the proton number 6 or the atomic number from the 12, and we know this has got 6 neutrons. So we know that 14 carbon is still carbon, and that this one must have 8 neutrons and this one must have 6. This is the radioactive carbon. You can't see that just looking at it. So most elements have what are called isotopes. Most probably have 3, 4, 5 different isotopes. Oxygen, you can have oxygen, 8 with a 16 mass number. You can have oxygen 17, you can have oxygen 18. So these are all isotopes. All have 8 protons. 16, 17, 18 means 8 neutrons, 9 neutrons, 10 neutrons. Isotopes is what they are. And they have different properties, and usually one of them will be the main one. And usually there'll be the odd radioactive isotope, even for these elements like carbon and stuff like that. So we can do what are called equations. Now there's a few other symbols we should know. We've met the alpha particle already. That one was the alpha particle. We're going to meet today what's called the beta particle, which is it is like that. So that's a beta particle. It's actually an electron. So it doesn't come into the mass part, but it does come into the charge part. It has a charge of -1. We're going to also meet the neutron and the gamma ray. Now, there are 3 types of radiation, and I'll just let you know about those before I actually look at some nuclear equations. There is alpha rays, which are alpha particles. There are beta rays, which are these high-speed electrons. They're not valence electrons, but they are electrons, so that you can't tell them apart. But they're actually from the breakdown of a neutron, but we'll look at that. Beta particle. And we've got gamma rays. Gamma rays are electromagnetic rays, and they are very, very short wavelength, high frequency, highly ionizing radiation. We'll look at these types of radiation in another video. For now, I just want to look at nuclear equations. So let's start with an equation where we have something called alpha decay. Now, we've got different isotopes of uranium. Uranium can be 235. Uranium on the periodic table is 92. So it can break down and give an element and an alpha particle. Now the way you do equations, so at the moment I'm not writing down what element this is, but we can write down the numbers. And the way we write down the numbers is by going, the mass numbers on both sides must add up. So 238 must be equal to the mass number here plus the mass number here. So you're all going, that must be 234. And these numbers down at the bottom must add up. 92, 2 plus that number. So I think we're all guessing that must be a 90, right? If we look on our periodic table, I think we end up knowing that that is thorium. And so we've done our first nuclear equation, which was actually an alpha decay. We'll show you in class some of the cool decay series that we can get. We can also have a different type of uranium, uranium-235. This is more the uranium which they use in nuclear bombs. This uranium, if you bombard it with a neutron, we just saw the symbol for that, it can break down. It does something called fission. And again, they might give you questions where they give you some of these numbers and you've got to make them all add up just like you did up here. And so barium, which they use medically, has 56 protons. Krypton, the old kryptonite stuff, it's not kryptonite, has 36. And barium has 141 mass number. and 92 as a mass number. 36, 92, 56, 141. Okay, so we could work out the neutrons here. That's not what I'm going to try to do. But if we add up these numbers, we've got 235, 236. We have to have on that side 92. Neutron, you can see it's not got no protons, so it's just a mass of 1. 141 and 92. Let's add these up. 141 plus 92 plus 1. We've only got 234, and we need 2 more. So we have to multiply this by 3 to make all the numbers add up. And when you put a number on the outside like this, it multiplies this one and this one. So this gives us 3 plus 92 plus 141 equals 236. So this is a fission reaction. Fission, splitting. A big nucleus splits into 2 smaller nuclei, daughter nuclei, and releases 3 neutrons. The thing about this reaction is that it's very easy for this reaction to keep going, because if this is a whole bunch of uranium-235 and 1 neutron kicks it all off, 3 neutrons get kicked out of the reaction, and if it's all surrounded by 235s, it can then cause more fission to take place, and every time you get a couple of extra neutrons produced. So this can be called a chain reaction, and it produces a huge amount of energy, and thus if you get a certain mass, you get a bomb. Critical mass is what that's called. Chain reaction and critical mass. And that's how they made the first atomic bomb. The thing is that this isotope is not common, maybe 1%. So you've got to get it out of the uranium ore, and they use a centrifuge. Very difficult, because the properties of these two guys are so similar. It's very difficult to separate this one out to make your bomb. This is what Iran has been doing for a few years, getting all these centrifuges so that it can do it, so that it can make its own nuclear bombs. But a lot of countries think it's unfair for other countries to have nuclear bombs, and therefore want to stop them. It's okay for them to have them, but not other people. So what other reactions have we got? We've got a beta decay. And the beta decay, I'll give you this example. This is carbon-14, the radioactive type of carbon. This carbon can break down and release a beta particle. Now, the beta particle, if we add up these numbers again, like we do, 14, 0, nothing there. So this one must be 14. But how do we go from 6? To get 6 over here, if we've got -1, this must be 7. We've got 7 and -1, 6, everything's cool. But 7 is nitrogen. So carbon has changed into another element. Alright, this is the whole thing that everyone was looking for in years gone past. How do we change things? So what's happened here is this one has got 8 neutrons, and this one has got 7 neutrons. But this one has got 6 protons, and this one has got 7 protons. So a proton has changed into, a neutron has changed into a proton and released an alpha particle, telling us that a neutron must actually be a proton and an electron together. Alright, and it's released this beta particle. I'll talk a bit more about those beta particles. The last thing I want to talk about is gamma. Now, when a nuclear reaction takes place, and you end up maybe with, I don't know, you can end up with a different type of uranium or what have you, but let's just put it this way. Let's just use uranium-235 and 92. That can go to uranium-235 and 92 plus gamma. The numbers add up, no problem there, because the gamma particle doesn't carry mass. It is an electromagnetic wave, EMW, electromagnetic wave, high frequency, high energy, short wavelength. just like light. But it does carry energy, according to E equals hf, which is something we actually do in year 13. It carries energy. The nucleus has rearranged and released energy. So we haven't lost any particles here. We've got the same particles, but we actually have lost some mass, because as we will learn, E equals mc squared, or energy is equal to mass times the speed of light. So that's how you do the equation there. I'll talk more about the mass thing in another video.